All right, today we're going to crack open the digital toolbox. We're going to take a look at some of the really elegant, really powerful ways that computers solve problems that, well, they don't have a simple answer. Problems where they have to kind of hunt for the solution, piece by piece. So it all kicks off with a question you've probably never even thought to ask. When you punch in square root of 2 on your calculator, how does it know? I mean, it doesn't have a massive phone book with every number in its square root, right? Nope. It actually runs a brilliant little algorithm to hunt down the answer. And here's the really clever part. The calculator completely reframes the problem. Instead of asking what number times itself equals 2, it flips it and asks, okay, for the function x squared minus 2, where does the graph hit 0? And if you look at this chart, it's that exact spot where the blue line crosses the horizontal axis. That crossing point is called a root, and that right there is our answer. So that's our first mission, find that root. To do that, we've got to pull out the very first, kind of most basic tool from our algorithmic toolbox. Okay, so this first tool is called the bisection method, and you can think of it like a trusty old handsaw. It's not fancy, it's not super fast, but you know it's going to get the job done. The idea is really simple. First, you trap the answer between 2 points, one where the result is negative and one where it's positive. Then, you just chop that space in half. You check which side the answer is on, and you toss the other half out. And you just do it again, and again, and again. And this visual here shows that whole process perfectly. See those points, P1, P2, P3? Each one is the new midpoint. With every single step, that search area, that bracket holding our answer, gets cut in half. You're literally squeezing in on the solution, narrowing the field until you're so close that it's good enough. It's methodical, for sure. It's reliable. But yeah, you can see how it might take a while.
Right, but what if we want to get there faster? I mean, who wants to use a handsaw when you could have a power tool, right? Well, it's time to bring out the big guns. It's time for an upgrade.
And this is the question that changes everything. Instead of just blindly chopping our search area in half, what if we can make a smarter guess? What if we could actually use the shape of the curve to our advantage to figure out where that root might be? Well, the answer is a huge yes, and it's called the Newton-Raphson method. And honestly, this is just pure genius. It uses a little bit of calculus to find something called the derivative. But don't worry, that's just a fancy way of saying it finds the exact slope of the curve at whatever point you're on. Then it draws a straight line following that slope and just sees where that line hits 0. And boom, that spot becomes your next and way, way better guess. And you can see it right here. We start at our first guess, P1. But instead of taking a tiny step, the algorithm looks at that tangent line, that straight red line, and takes this massive leap all the way over to P2. And look how close that gets us to the real answer in just one jump. It's not a guess. It's an incredibly educated prediction based on which way the curve is heading. Okay, so when you put them side by side like this, the difference is just night and day, right? On the left, bisection is the slow, steady march forward. On the right, Newton's method is like a series of powerful sprints, just leaping across the graph. I mean, they both get to the finish line, but one of them gets there a whole lot faster. But what if calculating that perfect slope is really hard, or even impossible? That's where another tool comes in, called the secant method. It's a really clever workaround. Instead of calculating the perfect slope, it just draws a line between the last 2 points it found and uses that as an approximation. It gives you most of the speed of Newton's method without all the heavy math. Think of it like a cordless drill, almost as powerful, but way more flexible. So we kind of know intuitively that some of these tools are faster than others. But in computer science, kind of fast isn't good enough. We need to be precise. So how do we actually measure that speed? Well, we talk about something called the rate of convergence. The bisection method, our handsaw, has what's called linear convergence. That just means your error gets smaller by a steady amount each time. Predictable progress. But Newton's method, that has quadratic convergence. And this is the real game changer. It means the number of correct digits in your answer roughly doubles with every single step. It's not just faster, it's exponentially faster. And you can see that insane power right here in the numbers. Look at this. We start with a guess of 1. The next step gets us to 1.5. The one after that, 1.416, getting closer. But then look at the very next step, 1.414216. We went from maybe 1 or 2 correct digits to 5 correct digits in one go. That right there is quadratic convergence in action. It's just incredible.
All right, so now that we've got these amazing tools for finding where a function hits zero, we can actually tweak them to solve a totally different but related problem, finding the highest or lowest point of a function. And this, my friends, is the world of optimization.
So yeah, the goal is totally different now. We're not looking for that zero crossing anymore. Now we're trying to find the very bottom of the valley, the minimum, or the absolute peak of the mountain, the maximum. And this is a huge deal. This is behind everything from training the AI on your phone to figuring out the most efficient shipping routes for a global company.
And our main tool for this job is something called gradient descent. The core idea is so simple and intuitive. Imagine you're standing on a hillside in a thick fog, and you want to get to the bottom of the valley. What do? Well, you look at your feet, find the direction that goes steepest downhill, and you take a step. That's it. That's literally all gradient descent is. You just do that over and over, and you'll eventually find the bottom.
And you guessed it, just like before, there's a Newton's method for this too, a supercharged version. Instead of just looking at the steepness, it also looks at the curvature of the valley, basically how much the hill is bending. And by using that extra information, it doesn't just take a step downhill, it tries to predict where the exact bottom of the valley is and takes a giant leap towards it. Again, much, much faster.
So this brings us to what's really the main point of this whole toolbox idea. We've got all these different methods, right? But how do you pick the right one? Well, it always comes down to a fundamental trade-off. And believe it or not, it doesn't even stop with Newton's. There are even faster methods, like Halley's method. This one is so powerful, it has cubic convergence, meaning the number of correct digits can triple with each step. But, and this is a big but, that incredible speed comes at a price. It's way more complex, and it needs even more information about the problem to get started. So what this all means is that there's no single best tool in the box. It's always about picking the right tool for the specific job. Are you working on something where you need the slow but absolutely guaranteed result of the bisection handsaw? Or can you afford to use the blazing fast power drill of Newton's method, knowing it might jam if you don't start it in just the right spot? It's always that same trade-off, speed versus reliability versus complexity. And that really leaves us with one final big picture thought. This trade-off, it isn't just for math problems. It's a fundamental choice that we see everywhere in technology. Think about financial trading, self-driving cars, the huge AI models we're building. Every single one of them forces us to make a choice. Do we go for the fastest, most powerful, but maybe more fragile solution? Or do we choose the slower, but more robust and reliable one? It's the algorithm's dilemma, and it's a choice that defines the world we're building.